Okay, morning everybody. Today we're going to carry on looking at vectors. Particularly today we're going to be looking at the vector of equation of a line and how we can use that together with planes to find out some interesting things. The first thing I'd like you to do today is, can you find the point of intersection between this line here and this line here? You don't need to know anything about vectors, it's just GCSE knowledge this. Pause the video, come back to me once you've done it please. Okay, so some of you may have done this by elimination. Some of you may have lined it up like this because that's the most common thing that you do at GCSE and quite often at A level as well. You'd have then times the bottom one by 2 and then took one off the other. So if you times this one by 2, you're going to get 5x equals 5, which gives me x equals 1. And elimination always works, it doesn't always work, but it generally works quite well, especially if the numbers are nice. But substitution is quite often the fail-safe method. Substitution never always works. So what I could do is substitute the second thing into the first one to find the value of x. So that would give me, by substitution, 5x plus 2 times 5 over 2 equals 10. That gets rid of the y, and so 5x plus 5 equals 10, and so x equals 1. So to find a point of intersection of two lines, I can do it by elimination, or I can do it by substitution. Okay, so let's have a look at another example. Okay, so that idea in mind of substitution works. What we might be asked to do is find the point of intersection between this vector equation of a line here and this plane. I think we talked about this previously, that pi is the normal letter we use to signify a plane. So here's a line, here's a plane. So because we can do this by substitution, we could think about substituting this one here into, so the line into the plane, and in order to do that we need to find values for x, y and z. So we can do that from here. We know that x is equal to 2 plus lambda, y is equal to 3 plus 2 lambda, and z is equal to 4 minus 1 lambda. If I substitute all of those into here, I'm going to get an equation which has just got lambda in it, and then I can solve to find the value of lambda that's required. Have a go at doing that and think about how you're going to use that value of lambda to find the point of intersection. Okay, so by substituting all of these things in here, you're going to get 5 lots of 2 plus lambda plus 3 plus 2 lambda minus 4 minus lambda equals 1. And if you tidy all of this up, you should get 8 lambda equals minus 8. Is that right? 5 lambda? Yes, it is. And therefore lambda is equal to minus 1. So we know that if I stick the information from the line into the plane, it tells me the value of lambda, which will it tells me the value of lambda for the point of intersection. So if I now stick that lambda back into my line, I know what r is equal to. R is equal to 2, 3, 4. Lambda is negative 1, 1, 2, minus 1. So altogether that gives me 2 minus 1. 2 minus 1 is 1. 3 minus 2 is 1, and then 4 minus minus 1 is 5. Therefore the point of intersection is 1, 1, 5. this was at lambda equals -1. Okay, so that's quite a nifty way of doing things, and it all comes back from the idea of substituting one thing into another. Can you, before we do anything else, can you just do the first parts of exercise 1.2 question 2? So do the part where it says find the point of intersection of the line and the plane. Do part 1, part 2, part 3, part 4 of those, and then once you've done those, come back to the video and we'll talk about how to find the angle between the line and the plane. Okay, hopefully that all went fine. Let's have a look at finding the angle between a line and a plane. In this diagram here, I've got a plane. I've got a normal vector of the plane. Remember, these can be just about anywhere. And I've got this line that's below the plane. That's puncturing through the plane. And here the line is going across the normal vector. So before we go any further, let's just remind ourselves of something. If we have two vectors, let's call this vector A and call this one vector B. Then the angle between these two vectors, theta, is connected by the equation A dotted of B is the modulus of A times the modulus of B cos theta. In other words, the dot product or the scalar product. So, in this particular example, we've got a right angled triangle which has been made by the projection of the line onto the plane. This normal vector coming up, and this and the line coming out of the plane. Sorry, I'm getting a bit lost where I am now. I keep getting interrupted. So I think I said that we've got the projection of the plane here, the projection of the line onto the plane. We've got the line coming out. We've got the normal vector. This makes a right-angled triangle altogether, and the angle between the line and the plane is this angle here. So it's the angle between the line and the projection of the line onto the plane. When I say projection of the line, imagine standing right above the line, shining the light. And if the line had some sort of thickness, it would make a shadow on the plane. Okay, so we can use these two ideas together. So if I do this dot product here, it's going to find me this angle up here, which is obviously the same as that angle in there. If you don't quite believe me about the dot product finding this angle, imagine this normal vector being over here. This normal vector being over here would give you exactly this situation, and because you'd have the vector coming out here, so you'd have the angle between this and the line, and then obviously you could just do 90 minus it. We're doing a very similar thing. We're going to find this angle, and if we do 90 minus alpha, we're going to find theta. So this is the idea. If I've got the normal vector and whatever this vector is, I should be able to find this angle theta in here. However, it's really important that you think about what the vector of the line is. So obviously L1 would be defined as R is equal to A plus lambda D. Now remember what we talked about in the first lesson. This thing here gets me to the line, but this thing lets me move up and down the line. D for direction, it's the direction of the line. So the vector that I would use to dot with the normal is not all of this together, it is just the D bit. It's just the D bit. And if you think about this a different way, I could have so many of these lines with the same D vector, but with different A vectors, but they would all create the same angle with this plane, because they would just puncture in a different place, but their direction would still be the same. So it's important that you dot it with the D not with all of this or with A or anything else. We're dotting the normal vector of the plane with the direction of the line D. So let's have a look at an example. Okay, so you're looking at these two things. Before we do anything else, we take the information that we need. The normal vector to this, remember this from earlier in the year, the normal vector, or a normal vector to this plane, is the coefficients of the x, y's and z's. So a normal vector is 3, -1 and 1. And the direction vector of this is 1, 3, 2. So I've got those two things together, so I can dot them. It doesn't matter which order I dot them in, so don't worry too much about that. So if I've got D dotted with N, that is equal to the modulus of D, the modulus of N, cosine theta. Okay, so what do we get from here? Well, if I dot these two things together, well, actually, let's write them out. We've got 1, 3, 2, dotted with 3 minus 1, 1. And then I've got 1 squared plus 3 squared plus 2 squared times 3 squared plus 1 squared plus 1 squared. Remember, you can just get rid of the minuses when you stick them in here because they'll be killed anyway. Times cosine of theta. Okay, so at this point, quite often people get themselves in a bit of a tizzy because they've written this down and they've written this down. I've got a theta here, and then it doesn't really make too much sense because actually what we're finding is alpha. Theta is the angle between it. We're not actually finding theta at the moment. Okay, so make sure that you do actually substitute alpha in for this, because otherwise it might not make too much sense, or worse, you'll get to the answer line and you'll see theta equals this and you won't do the 90 minus to get your actual answer. So if I dot these together, it's 1 times 3 plus 3 times minus 1 plus 2 times 1, which is 2. And this one is 14. And that one is 11 times cosine of alpha. So alpha, if I rearrange this, is going to be cos minus 1 of 2 over the square root of 14 times 11. So alpha is going to be 80.7 degrees. So that gives me this angle here, that alpha there. That alpha there is the same as what would be in here, thinking about from corresponding angles. And so if I want to know what theta is going to be 90 degrees minus 80.7 degrees, which of course is just 9.3. So what I'd like you guys to do now is go back to question 2 and do the second bits, finding the angles between each one. Once you've done that, can you do questions 4 and 5? And I think that should be sufficient. Yeah, just questions 4 and 5. Okay, hope that all goes well, and I'll speak to you guys again tomorrow. Bye-bye.